Yeah, thank you for the invitation to speak here. Thank you for the kind introduction. This is actually my first time at JHU, very much like the campus. Excited to meet the rest of the faculty, hopefully. As Najim said, I am a program manager at DARPA. That's the Defense Advanced Research Projects Agency. And we are the risk-taking arm of the Department of Defense. So you oftentimes hear entities saying, oh, we like to take risk. We're the risk-taking arm of X, which is what we used to say at the Air Force Research Lab. But DARPA actually means it. DARPA is one of those rare places where people expect you to fail because they want you to take big enough risks that merit such failure. And so to that end, I've been trying to grow the neurosymbolic AI portfolio of programs. The first of its kind is ANSWER, Assured Neurosymbolic Learning and Reasoning, for which I am the program manager. And today I will talk about two others that look at foundation models for autonomy and foundation models for scientific discovery. And so before we get into that, I want to touch on some background, just so we're all on the same page about what I mean by foundation models. And then I will talk about how the landscape of challenges and opportunities has really dramatically changed in the past year since the release of Chat-GPT, why DARPA cares, and perhaps where DARPA should be investing. So in the spirit of that, whenever I give a talk, I like to tell students, faculty, anyone in the audience, that if you have any really great ideas that you think government should be investing in, please do feel free to reach out. So to start off, what do I mean by a foundation model? When I say foundation models, I'm talking about typically large pre-trained architectures. These are usually trained in a self-supervised manner over very diverse pieces of data, such that it can be efficiently fine-tuned to some downstream task. So of course, Chat-GPT and that whole line of GPT models is an obvious example of a foundation model for language. You take very diverse pieces of text data from things like web crawl, Wikipedia, speeches, exams, etc. You train them using self-supervised training, things like mass language modeling, next token prediction. And then you can very efficiently fine-tune to your downstream task by in-context learning, chain of thought reasoning, all kinds of methods that have become popular in the past year. Now, when these models came into prominence a year or so ago, there was a lot of buzz at DARPA and elsewhere about how we should be leveraging these models. What's interesting is that in the past year, a lot of the challenges have shifted. So when Chat-GPT first came into prominence, the estimated costs to train such a model were tremendous. There were estimates that this could cost over $100 million just to train these models. And so from a DARPA perspective, it didn't really make sense that we should train our own model. But in the past year, we've seen this nice rise of scaling laws, which come from DeepMind's Chinchilla paper and a lot of follow-on work, where there's some very simple insights that can significantly reduce the costs of training LLMs. Some insights are as simple as scaling the size of your training data as you scale the size of your models. This is sort of the original insight of the Chinchilla paper. And then there's been a tremendous amount of follow-on work. And so now we're at a stage where we could reasonably consider training our own models from scratch if we wanted to. The cost is permissive enough. Now, when we do train this model, we then face a different kind of challenge, the cost of inferencing, because typically these models are very large and it's actually quite expensive to inference on. So there are estimates that the daily cost of inferencing for Chat-GPT is up to $700,000. Clearly, this makes it intractable for a place like DARPA to make an investment. And at any rate, industry has tremendous incentives to bring this number down. So why should DARPA invest here in the first place? I argue that we shouldn't. I argue that we can just take the latest and greatest from industry. And industry is actually making tremendous advances here by developing increasingly smaller models that are very effective. So you might be familiar with Llama 13 billion. I believe there's also a Llama 7 billion. There's alpaca. There's all kinds of models at under 10 billion parameters, which is fairly small for a foundation model. And of course, because they're smaller, they're a lot cheaper to inference on. But we also see that there are ways to almost replicate the performance of these large models. So there's this notion of model distillation, for example. I think maybe the most famous example of this is the alpaca model, where you can take a large, or not so large, a 7 billion parameter llama model, and fine-tune it on self-destruct tasks from a much, much bigger model like Chat-GPT. And this 7 billion alpaca model will perform similarly to this much, much larger, 2 orders of magnitude larger foundation model. We've also seen not just this form of distillation, we've seen low rank adaptation, where we can treat the fine-tuning of foundation models as a low rank factorization problem, which is very easy to solve, or rather very cheap to solve. And we've seen all kinds of other very efficient methods. Again, all of this in the past year. A lot of these results actually come from the supposedly leaked Llama 2 weights back in January or February time. As soon as these were leaked, open source community, academics, a lot of people developed very impressive, efficient fine-tuning methods, in part, I would argue, because they don't have access to the tremendous amount of compute that industry does. And so as much as academics like to complain about not having access to enough compute, I think it is that constraint that really sort of catalyzes innovation in this space. Now, given all of this, we revisit the question, where should DARPA be investing? Typically, when we consider selling a program at DARPA, we have to set ourselves apart from industry. And so there are at least 4 key pillars by which we try to set ourselves apart. In terms of data and compute, industry tends to have access to huge amounts of data. And so they can leverage tons of compute, tons of data. Their life is a little bit easier than in the DoD, where we have very limited data. You might imagine, for example, that if you want to detect some military sensitive vehicle, there might only be a small hundreds of images of that vehicle out in the wild. This is severely constrained when you compare to large data sets like obviously ImageNet, etc. Now, increasingly, this is a line that is getting blurred by foundation models, because in principle, we could pre-train a foundation model on industry's large amount of data and efficiently fine-tune on the DoD's limited amount of data. Another distinguishing factor is the fact that, of course, industry is profit-driven. DoD, we're not trying to make a profit. We are what we call purpose-driven.
Access to data. So are you throughout the talk focused pretty specifically on language data?
No.
So then I would imagine DoD has access to reams of sensory information.
They do, but it depends which domain you're focusing on. So if you focus on, and I'm going to get to this, areas like sequential decision making, where you're using simulation environments to generate your data, there the government faces serious limitations in terms of how quickly those simulations can generate that data. Yeah. And some data, I mean, there are a lot of restrictions here when you think about it. Some data can be classified. It's hard to get access to. And even for image data, you would think we're drowning in image data. We're actually not. We're very limited in terms of image data. Some domains, I know RF, we have some decent amount of data in RF. Electro-optical, more or less. But people tend to think that we have just this store of huge data sets. We don't. In terms of consequences, this is another key distinguishing factor. In industry, the consequences of a failure are generally low. You know, if your large language model, you prompt it, it says something rude or mean, that's unfortunate. It's not a big deal. In the DoD, if you have, for example, a classified large language model, and it tells someone who doesn't have the proper credentials some classified information, that can be disastrous. So there's this big challenge of how does one even establish a classified LLM? And that has all kinds of interesting challenges. Finally, the threat models are very different. Industry faces, of course, your standard commercial adversaries, perhaps the occasional hacker. DoD faces nation-state level adversaries that can launch dedicated campaigns. And so this is, again, another area where our sort of interests are very different. So we typically use this kind of thing to motivate where DARPA should be investing. And I want to talk about two areas that meet this criteria. So first, we have the TMAT program. This is one of my latest programs, transfer from imprecise and abstract models to autonomous technologies. And here the premise is fairly straightforward. You might imagine that if you want to develop a foundation model for autonomy or for sequential decision-making, that you would want to, again, train this on very diverse data. In this context, your diverse data would be diverse simulation environments that generate the data. So for example, here we have Deep Racer, Grand Theft Auto, Carla. We could throw grid worlds on there. We could throw 3D world, all kinds of diverse simulation environments. We would train our foundation model, presumably using self-supervised pre-training. And then we would transfer that learned autonomy to the real world, where, of course, we realized that things look nothing like our simulations. So we would need a feedback loop. We would leverage the data in the real world to refine our foundation model, to refine our simulation environments, etc. Why is this a challenge for DoD? Going back to your original question, it's the fact that our simulation environments are incredibly slow. So here I've listed what I think are the three most popular simulation environments across the Department of Defense. We have AFSIM, which is the Advanced Framework for Simulation, Integration, and Modeling. We have OPSIM, which is what the Army uses. And we have AWSIM, which is what the Air Force uses to simulate their big plans, what are called air tasking orders. Now, each of these runs on the order of minutes to hours for a single execution, to generate a single piece of data. And when you couple that with the fact that the state of the art in areas like sequential decision-making require millions of executions, you do the math, it can take years to learn the relevant autonomy if we use these sims. Yes?
Can you give a rough idea of what an episode corresponds to here?
Yes, an episode here corresponds to, in the case of AFSIM, a 3 versus 3 engagement. It's a fairly small. The part of the problem here is that these models use very precise flight dynamics models. Their communication structure so that entities can communicate with one another impede a significant speed up. And they model, curvature of the Earth. They model all radar signal degradation. All of these models are very rich. And so it's very hard to speed things up significantly. Yes.
Distributed architecture speeds up, for example, scanner across 100 sheets.
Well, not 100 times faster. So the scaling laws in a lot of these areas don't scale linearly. You could absolutely do a distributed implementation, but in areas of sequential decision making, like planning and reinforcement learning, you don't get that kind of linear speed up. So it would help, but it wouldn't be enough to solve these issues. And then we face even more problems. So let's say we did train this autonomy successfully in simulation, and now we want to put it on a physical platform. Then we face what are known as the sim to real gaps. So these are sort of the discrepancies between what we model in simulation and what we know how to model things perfectly. So here I have one example. This is from the DARPA Machine Common Sense program, where Oregon State University, this is Alan Fern's group, very popular roboticist. They were training this Cassie bipedal robot to run while balancing 2 containers. Naturally, you want to train it in simulation first because it's much faster. You don't risk damage to your platform. And so here they have a Mojoko-based simulation. And if they model everything at very high fidelity, if you model your friction coefficients at very precisely, your joint dynamics, you have precise mathematical models of your containers, then you can successfully do this kind of transfer. And so they learn how to run in simulation, and the real life robot can run about 96% of the time. But what happens if you increase that sim to real gap just a little bit? Let's say we're still modeling everything at very high precision, except for the models of the containers. Then the performance plummets to 0.1%. So this is an example of how pernicious. Consider something. This is actually a fairly simple problem. CASI does not have a vision stack. CASI is a sensory motor proprioception problem. It's inherently a low dimensional control problem. And we've imposed a lot of structure in our environment. We understand this environment very well. We can model it very well.
So the model for the containers, the first one presumes rigid structure, and the second one they can wiggle around.
Mhm.
Is that what it is?
Yeah, yeah. And even, I mean, I wouldn't consider that to be a large sim to real gap. It's enough to completely break this. Yeah. And in the case of, you know, the Department of Defense, if we ever want autonomy to explore the deep sea floor or explore some unknown environment, clearly we're going to face much larger sim to real gaps than this. We're going to have vision. We might have adversaries. There are external events we have to consider that increase these gaps. Oh, my hope, and I'll get to that, but my hope is that across the proposals that I'll receive on December 20th, will cover the entire gamut from perception to high-level planning to low-level control. Yeah. So how might we achieve this kind of fast and robust sim to real transfer? We can begin by making the observation that even very different looking environments can nevertheless share some kind of underlying semantic abstractions, and that we might leverage those abstractions to come up. So here I have a toy example. This is not real. This is for illustrative purposes. But let's say we have a robot going around some building, doing perhaps slam or some kind of task like this, and we wanted to know what a door is. Maybe it's too expensive to train a door detector in the real world, so we want to use a very, very simple environment. So here we have mini grid. Mini grid is on the order of hundreds of pixels. You could run many, many simulations in under a second. But you'll immediately notice that doors in mini grid look nothing like doors in the real world. A door in mini grid is a yellow square. You interact with it, it turns into a yellow line. So clearly conventional transfer learning wisdom goes out the window. We can't just train pictures of mini grid doors and expect that to transfer. To semantics of what it means to be a door are nevertheless preserved across these two environments. We can say that a door is some kind of movable barrier that is housed inside a larger non-movable barrier, which would be your wall, such that when you interact with it, you go into some new area. Why is this useful? It's useful because it gives us new learning directions by which we can ground our concepts. We can learn what it means to be movable or non-movable through interactions with the environment, a functional kind of grounding. We can learn what it means to move into a new area by observing a high amount of entropy associated with being in a new area. And so now, when we transfer this representation to the real world, first of all, we might be able to do it more quickly because we've learned a lot of this grounding in a much simpler, much faster environment. But we should be able to do it more robustly, because now to fool the real world robot as to what a door is, you would have to fool the vision stack, the functional grounding, and the information theoretic grounding. And so we argue that by leveraging these shared semantic abstractions across diverse simulations, that we could actually achieve this kind of fast and robust transfer of autonomy. And so that informs the program vision, that we can start from very low precision, very abstract environments, and that we can transfer not just to the real world, but perhaps even to increasingly higher fidelity environments. We also explore the reverse direction, which is as we collect data in these higher fidelity environments in the real world, that we can leverage that data to refine our simulations, our models, our abstractions. So we're exploring both directions here. Now, in terms of the program context, where this falls in the autonomy landscape, here I've listed some DARPA programs that are doing autonomy, as well as what industry is up to. So to start with the DARPA programs, I have to first point out that a lot of people that claim to be doing autonomy are actually doing automation. They're doing things like prescribed rules. So for example, a lot of the work you see in autonomy for controlling some kind of platform usually revolves around doing things like object detection or waypoint navigation. And the control of the actual platform is deferred to more classical methods of control. So that's closer to automation. It's harder to adapt in the real world because you have some sort of prescribed rules. And of course, classical control methods are less adept at handling uncertainty. They're very good in controlled environments, but they're less adept at handling uncertainty. The two programs at DARPA that I would argue are doing real autonomy are ACE and AIR. AIR is a brand new program. But the challenge here is that these programs are using the AFSIM simulation that I mentioned earlier. And so by the program manager told me it takes them about 2 months to learn their underlying autonomous capability, which is usually controlling some kind of aircraft. And it takes them 2 weeks to adapt to a change in the environment. So this is not good for real-time adaptation. Again, we're hoping to do much better because we're leveraging lower fidelity environments that are much faster as opposed to using AFSIM. And so that's how we set ourselves apart at DARPA. How we set ourselves apart from industry is something I've alluded to before. So when I say autonomy, of course, everyone, I think, immediately thinks of autonomous driving. So what are they doing in that sector? As I was preparing for this program, I had to read a lot of Waymo technical safety reports to see what they're up to. And what they do is they generate over 20 billion miles of simulated data, over 15 million miles of real world data, but they're not using this data to learn how to control the vehicle. They're using this data to generate predictive models for pedestrians and other vehicles, and then they deploy their vehicle autonomy based on object detection and more classical control methods in a geofenced area where they have the right sensor placement, where they understand the infrastructure, in the right weather conditions, etc. And so
when you talk about classical control, you include things like model predictive control.
Exactly, that's right. And so as impressive as autonomous driving is, they have to impose a lot of control, a lot of structure on the problem domain to make it work, which makes perfect sense in their settings. Again, in the DoD settings, we don't have that level of control. If we're going to map out the surface of the ocean, we can't control the surface of the ocean. We don't know what that looks like. There's no way to really geofence these things. If we're going to deploy these autonomous platforms in unknown environments, we don't have that level of control. And so I suspect that we'll need entirely different methods than what industry is developing. So again, just to reiterate the goal, we want to develop these fast and robust methods of transferring autonomy. Here I have a very simple example from a sequential decision-making problem. At the top, we have Deep Racer, which is a very abstract racing simulation. And here, the states or the observations the agent can make are very simple. It's the view from your windshield, your front view. The actions are very simple, very abstract. You can throttle at 1 or 2 meters per second. You can steer by 15-degree increments. The transition dynamics are defined in the obvious sense. This is how the simulation evolves as the agent interacts. So of course, if you turn to the right, next time step, your car will be on the right. And finally, you have rewards, which are basically, so if the agent wants to get to the finish line as quickly as possible, the obvious reward would be to provide a small penalty for every action that does not lead to the finish line, and a huge reward when it reaches the finish line. Based on that reward, that reinforcement signal, the agent in principle can learn how to race in this track. But let's say we have done that. Let's say we have this great racing agent, and now we want to transfer it to the real world. Immediately, we encounter huge sim-to-real gaps. The real world looks nothing like 3D Racer. The texture of the road is different. The visual cues are different. The actions are very different because, of course, we don't turn our steering wheel by 15-degree increments. We turn along a continuum of values. The transition dynamics are different, and even the rewards can be different because maybe now we don't just want to get to the finish line as quickly as possible, but we also need to obey rules of racing and so on. And so in this context, we have sim to real gaps in terms of everything: states, actions, rewards, transitions. So it's worth thinking about, how does one even derive the underlying, what I call semantic anchors, those semantic abstractions that remain consistent across environments? How does one do that for states, for actions, for rewards? And then the second question is the reverse direction. Once you are in this real world and you collect data, how do you then use that data to refine the underlying models? Another thing we're interested in is, how do we even quantify these gaps? Because if we're going to make the claim that we're robust to sim and sim to real gaps, we should at least be able to quantify what that means. Right now, that's mostly an intuitive notion. If I show you two environments, you might intuitively say these look different, but we don't really have good ways by which to quantify how different they are. So that's something we're exploring. How do you quantify these? And in the reverse direction, how do you measure semantic similarity? Which is to say, as we begin to refine our simulations, how do we make sure that they're closer and closer to the semantics of the target environment, even though they might still look very different? And just to drive the point home about the importance of testing against these gaps, here I have, this is a fairly outdated paper called Deep Explore, very famous white box testing paper, where they take an NVIDIA DAVE 2 autonomous driving platform, and they train it in the source environment, and the agent can stay on its lane. But then if you darken the environment a little bit, it drives off the side of the road. So I want you to consider that this is a tiny sim-to-sim gap, and it still causes failures. Yes. Yes, that's a good point. I'm actually going to talk about that in 2 slides. So, and then so if you still have the question after that, then you can ask me again. So now I want to provide what the bases of confidence are that makes me believe that we're at a stage where we can actually address these issues. So if we look at the current literature, there's some hope that we can extend the state of the art to address these problems of robustness, speed, abstraction, refinement. Beginning with robust autonomy transfer, here we have what I think is by far the most popular method in sim to real transfer for robustness. It's called domain or dynamics randomization. And the premise here is very simple. You might imagine that in any good simulation environment, there's a set of parameters that you tweak to generate an instance of that simulation. Those parameters govern things like the placement of objects, the textures, the friction, etc. So the question under this domain dynamics randomization is, how do we optimally tweak those parameters to generate the most representative set of instances so that when we train over those instances, we're robust to the changes expressed therein? Very, very popular approach. This was actually used in that bipedal walking example that I talked about earlier, and yet it still failed catastrophically. So clearly it's very good for smaller gaps. It's not good enough for bigger gaps. But I would be very curious to see how we can bring things like these semantic anchors, these semantic abstractions, and use that to extend domain and dynamics randomization to make it more robust. Second basis of confidence comes from a paper I have in AAAI 2021, where we transfer across 2 very different looking environments. We transfer from a simple grid world to what is called a safety gym, a 3D world. So of course, the source environment is a grid world, discrete actions. The target environment is 3D and has continuous actions. But we nevertheless successfully transfer by leveraging a shared semantic abstraction of the reward signal. You might imagine that if you represent the reward signal using a formal language, then that reward signal can take on a structured form, in this case, a deterministic finite automaton, and you can learn relevant information over the transitions of that automaton and use that to transfer across different environments. So this is very different from more conventional transfer where you would transfer the parameters of a neural network. Here we instead transfer parameters of a shared semantic representation of the goal. As far as the basis of confidence for being able to transfer quickly, not surprisingly, this comes from large language models. In some sense, the fine-tuning to a downstream task is a kind of transfer learning. And there have been huge successes in transferring in this space. However, there's a sort of implicit assumption when it comes to language that makes things work as well as they do. And that's the fact that given any language, no matter how diverse the text is, there's an underlying lower dimensional syntactic semantic structure that they're conforming to. And so in this sense, something like the manifold hypothesis is satisfied. We can reasonably say that if we throw a large enough model at it, train it in a self-supervised manner, that it will learn sort of the structure of language. But what does that look like for things like sequential decision-making? What does it look like for scientific discovery? It's not clear. It's not clear that there's a lower dimensional syntactic semantic structure to the language of science, let's say. And so I suspect that we'll have to make these structures more explicit, which again goes back to these semantic abstractions. How do we make these semantic abstractions explicit and use them to help us transfer so that we can achieve a similar success in transfer that the language community has experienced? Finally, and going back to your question, the basis of confidence for being able to refine our models and our simulations, the most obvious basis of confidence here, I would say, is the world modeling literature. So this is a sub-area of machine learning that took off in 2018 with Google's Dreamer paper. And the premise is very simple. You have an agent, they're trying to learn how to play a game. Maybe it's too expensive to play the game in the real world, so we want to teach the agent to dream or imagine the game. So what you do is you have the agent play enough where it can recreate the game within its network. And you want that game in its network to be of a similar visual fidelity as the target and to have a reward prediction model. So you can train over your dreams or over your imagination. And there have been a lot of successes in the space, but I would argue that for my program, you wouldn't want to learn the target environment at a high level of visual fidelity, which consumes a lot of data. You would want to learn it at the right level of semantic similarity. And so what you learn might look nothing like the target environment, but it captures the underlying semantics, and because of that, should run much faster.
So essentially, you are not really training these models on pixels, which is really what everybody's trying to do.
Right. I wouldn't be trying to recreate it in a pixel sense. You would be consuming the pixels, but what you would be trying to recreate is a much lower dimensional, semantically similar. Yeah, right. So that's the main basis of confidence there. Another basis of confidence, this is from a couple papers my group published in ICAPS 2022 on learning a formal model of your reward signal. And so here what we did is we took a very old algorithm from grammatical inference known as L-star, which a lot of you might know about. And L-star, the classical version is actually very simple. You have an all-knowing oracle that can answer two questions. I can come to this oracle with a word, and a word doesn't have to be natural language. It's a sequence of letters. Each letter could be a meaningful event, like detecting a door or something like this. I go to this oracle, I ask the oracle, is this word in my language? Oracle says yes or no. You ask enough of these questions and you can generate a hypothesis language. You show this language to the oracle and now you can ask the second question. Is this the language I'm trying to learn? If the oracle says yes, you're done. If the oracle says no, it gives you a word that should be in your language that is currently not in your language. Based on that, you can ask more questions of the first kind, and there's this natural feedback. Very simple conceptually, very interesting mathematical properties for learning regular languages. But historically, the dilemma is, who is this all-knowing oracle that can answer these questions in the first place, right? It's a practical conundrum. In the case of areas like sequential decision-making, your reward signal is your oracle. You might imagine that if I'm trying to learn the language of chess, which is to say intermediate tactics that are conducive to winning the game, and I have a reward signal +1 if I win, -1 if I lose, I can formulate these same queries, membership and equivalence queries, to try to learn that language of chess based on that reward signal. And so that's basically what we did. We did that for reinforcement learning, in one of the papers, and we did it for planning in the other paper. And so in this way, you can leverage experience in your target environment to learn a formal semantic abstraction of the reward. And if that happens to be shared across simulations, you might even use that to do transfer learning. This is more of a programmatic slide, though. How are we going to measure success? We're going to measure it in the obvious way. You know, people give us their new transfer learning algorithms. We compare against the state of the art. We observe whether we're getting a better mission success rate. What's worth noting in this slide really is the fact that this program has two phases. So in the first phase, we're doing sim to sim transfer, because of course that's a lot more manageable when you're not dealing with real platforms. So in that sense, the source environment might be a grid world, Carla, whatever. And the target would be a high fidelity sim like Gazebo, Air Sim, etc. For phase two, we're doing sim to real. So then the target could be, again, Cassie bipedal walking robot, some legged dog, etc. And this I'm excited about. We actually have a competition under this program. For the sim to sim competition, we have prize money, $1 million for first place, $750K for second, $500K for third. This is money that you can spend however you want. Doesn't have to be on research. This is your money if you win it. For the sim to real competition, there's one grand prize, $1.5 million. And we're working on getting an autonomous Formula One car for this competition, actually. So that's very exciting. We have the associated low-level fidelity simulator called LGSVL, the high fidelity simulator, whose name I forget, and we have the physical car itself. So that's very exciting. And as we look even further out into the horizon, let's say we're successful in developing these models. The next question, I think, would be, what do they look like from a low swap perspective? From small size, weight, and power. Because when I envision an embodied autonomy developed in industry, I imagine some kind of robot that you can charge in the middle of the night, that is always connected to the internet. And so that means that energy is not really an issue. And training is not an issue, because if you're connected to the internet, the cloud can do all the training you want. It's a general purpose compute. But if you actually want to deploy these things in unknown environments with restricted communications, well, now you don't have access to that power source. You don't have access to the cloud, which means you have to be good at training internally within hardware.
And latency.
And latency as well. That's right. Yeah, usually in the DoD, we use the term DDIL. So that's the L is for latency.
Yes.
Deterred, intermittent, latent, restricted. Yeah, that's right. So this is debating whether to pitch a program in this space, but this is something I'm excited about in the long term. Finally, and very quickly, the second program is on foundation models for scientific discovery. The deadline for this was yesterday. We received a lot of interest. And this explores a similar question, but for a completely different application. Here, what we want to do is we want to take a foundation model that we can train on the multiple modalities of research literature, experimental results, simulation environments used for experiments, et cetera, and see if we can train it to generate creative hypotheses, to generate the experiments that would validate or refute those hypotheses, and that can leverage the results of the experiments to refine its knowledge base. Part of the motivation here is the fact that when you look at tools like AlphaFold, which is sort of heralded as the big marvel of scientific discovery, their inductive biases that are used to trim down the hypothesis space were brought in by humans. So for example, what it means to be a valid folding angle or an invalid one, what the van der Waals forces are that govern how parts of a protein interact with one another, what the electrochemical properties are that constitute a valid protein folding. All of that was brought in by human experts. We argue that in principle, the AI should either be able to identify all those inductive biases from the literature, or more excitingly, it should be able to derive them from first principles. So that's one part of it. The second part of it is, how do we even measure that these foundation models are being creative in the first place? Because creativity is not just novelty. There's a lot of useless novelty out there. So how do we measure computational creativity? Of course, the psychometrics community has been exploring this for God knows how many decades. And so it would be exciting to see how a collaboration between the machine learning community and the psychometrics community would lead to new metrics of computational creativity. And even more excitingly, how we could use those metrics to train increasingly more creative AIs. One of the obvious challenges here is that the more creative a hypothesis is, the less likely it is to be represented in the training set. So this is inherently a sort of out of distribution problem. So to conclude, of course, we all know foundation models have had tremendous successes for language and vision, but for other areas like sequential decision-making, scientific discovery, there are still huge gaps, and that's what we're trying to explore under these programs. We're exploring new architectures, new forms of self-supervised pre-training, new forms of fine-tuning or transfer learning to downstream tasks, etc. And finally, I wanted to plug DARPA Connect. This is a very good resource for anyone who has questions on how to collaborate with DARPA, who has questions on submitting proposals, especially first-timers. I know that the first time you submit a proposal to DARPA, it can be very overwhelming. So please do reach out to DARPA Connect at darpa.mil if you have any questions. And with